Hello everyone. In this session, I'm going to look at how neural networks can be used for regression purpose. Now that we already know how we can use neural networks for classification of the data, where we have looked at 5 different algorithms. Now we will look at how we can use neural networks for regression purpose where the objective is prediction of a numerical variable. So this is where I want to use the neural networks for. Again, we'll take up some kind of data set where the objective will be to predict a numerical variable, use the different algorithms of neural networks, try predicting the values, try creating the models from the existing data, and from them test out the goodness of fit of those models and get into the accuracy of the model, come out with mechanisms of accuracy of the model, and based on that you can shortlist which models are more and more apt for the data. So here in this context I'm going to look at 6 different algorithms. The first 3 are similar to the ones that we have looked at for classification purpose as well. The only difference being the data will be different. The response variable in the classification problem, the response variable was a binary variable, whereas in this case the response variable that I would be considering would be a numerical variable or a continuous variable. So that's the major difference. Otherwise, we can look at the resilient backpropagation with backtracking. Without backtracking, smallest learning rate. These 3 can very well be executed through the package neural net, with which we have done the classification problems as well. And even the formula that we would be using, the function that we would be using in this context is also neural net. The only thing is the algorithm. The algorithm in this function, we would be changing it to rprop plus in case of backpropagation with backtracking, rprop minus without backtracking, and SLR to go ahead with smallest learning rate. So we would be using that as well. But after that, the 3 algorithms that we are focusing are something that we did not handle in the earlier case. We would be looking at general regression neural network. We will talk about monotone multi-layer perceptron MLP models, and we will also talk about the quantile regression neural network. So these are the 6 different algorithms, and all of them we would execute on one single data set itself with the same set of elements going as a part of the training data and the same set going as a part of the testing data. And the data set that I want to consider for this purpose is the insurance charges related data. So which is there in my directory. I'm just loading that into R. So quickly looking at the dimensions of the insurance data, it has 1338 rows and 7 columns. Looking at the structure of this insurance data, it contains age, which is an integer, the gender of the person, male, female, factor with 2 levels, BMI, the body mass index, right? And it's talking about the number of children for that person, going from 0 to 3 kind of numbers, and then whether the person is a smoker or not, the region to which the person belongs to, northeast, northwest, etc. And this is the variable that is of interest for us. This is what I am calling as the response variable for this problem. I want to really predict what would be the typical insurance charges given the age, the sex, the BMI, the number of children, smoker status, and the region of a particular person. So this is the model that we want to build using the neural networks. So looking at the presence of NAs and etc., I can look at quickly the summary of insurance to see if there is any kind of a possibility of NAs present as a part of the data. I could see that no NA. Age is a number from 18 to 64. Sex, there are 662 females and 676 males, more or less uniformly represented. Region also, there are 4 different regions, more or less uniformly represented. Smoker status, there are 1064 non-smokers and 274 smokers in the data. So this is how the whole data is looking like. And now I want to go ahead in terms of fitting the neural network model for this kind of data. Right, I don't need to explain the package neural net and even the function neural net as well, because we have dealt with that in depth when we have talked about the classification problem. So here I'll directly use the neural net function. So just a quick recollection of the stuff. Here we are giving a formula y, which is the dependent variable. The dependent variable in this case has to be a numerical variable or a continuous variable. That's the main thing that I have to ensure out here. Then I have to specify the data, which is that insurance is my data. I have to specify how many hidden layers do I require, and I also need to specify what is the algorithm. So let me tell you here, I would take these three one after the other within the same models itself. So I'll first set rprop plus, indicating it as resilient backpropagation with backtracking. I would also fit one or two models with rprop minus without backtracking, and I would also set it as SLR, which is the smallest learning rate. We'll build all the three models simultaneously. So if you see the first three models that I'm talking of, these are the first three models. Almost everything is the same in terms of the slides. So what we can very well go ahead with is we will implement one of them. We will go through the slides of one of them, but parallelly we can very well take up rprop plus, rprop minus and SLR, all three of them into the model, and we can evaluate all of them simultaneously. Now, getting into the process, initially we have loaded the neural net package already. So let me we have to load it. So I don't want to install it, it's already installed. So I'm simply loading the neural net package. So the again, neural net as such as a function, I don't need to really talk about much, but just for people, if you want a quick refresher, neural net as a function, I need to specify the formula, right? It is training the neural networks using the backpropagation, resilient backpropagation, wherein a couple of other algorithms are being talked about. So here I have to give neural net as a formula, and I have to specify how many hidden layers are there. I can also specify the error function as well as activation functions. Here we had a flexibility in terms of error functions and activation. So SSE is sum of squared errors, that is what I would prefer here. And activation function, the logistic is the default, but apart from that it also supports tan H, which is the hyperbolic tangential. All other things probably we have talked about when we are working with the classification problem. So we will try to set a few different models. One, by changing the number of hidden layers, and two, playing around with the three different algorithms, rprop plus, rprop minus, as well as SLR. So with this data that we have, 1338 rows of data that we have, let me just see how much is the 70% of it. 70% of it is 937. So the remaining this 937 will be considered as a part of the training data. The remaining 401 will be considered as a part of testing data. So let me randomly select the 937 element. So I will set a seed value for 1000. Based on that, I will compute the train as a variable, which is a random selection between 1 to 1338. Randomly, I want to select 937 values where there is no duplication of the values, which means I am setting the replace equal to false so that the duplication does not crop up. And based on that, I am calling my training data, which is a subset of insurance, where I am considering only the rows that are there as a part of the train and all the columns of that insurance. Similarly, my test data is again a subset of insurance, wherein I am considering only those rows which are not there as a part of the train, and I am taking all the columns. So this way my training data as well as the testing data, both of them are in place, right? And again, my formula also is something that I am more interested in. So charges is the response variable for me. Tilde, I want to consider all of them. Charges is the response variable for me. Sorry. F is charges. Where is my response variable? Charges. Charges is the response variable. Tilde. I am looking at age as one of the independent variables or the explanatory variables. Then looking at sex, BMI, then children, smoker, yes or no kind of a status, and finally the region. So this is what is my formula. Now I also need the data to be scaled, right? I require my entire data to be scaled, especially the training data as well as the testing data. It's better that I scale them, but it would have been better if I have scaled the entire data rather than only the training data separately and the testing data separately. So that's the reason. Probably let me do the process again. I can very well put insurance as the scale of insurance. So here we don't have the numeric vectors for doing the scaling. So it's better that I convert them into numeric, right? So let me do one thing. Insurance 1. Let me assign everything in insurance to insurance 1. Now we'll create a few new columns. Insurance $1 mail. I'll create one variable called insurance $1 mail, where I'll take it as if else insurance $1 sex is equal to mail. If that value is equal to mail, I will set it as 1, otherwise I'll set it as 0. So this becomes a quantitative variable, insurance $mail. Similarly, now I'll go with the smoker. Insurance smoker, let me keep the name same. I'll call insurance $smoker, where again I'm saying insurance $1 smoker is equal to S. If that is equal to S, I will set it as 1, otherwise I'll set it as 0. So even this will become a quantitative variable. Similarly, region, I'll call this as insurance $1 northeast. That's the name I give any. Any is standing for northeast. Again, I can set if else. I'll say insurance $1 region is equal to northeast. I'm setting it as 1, else I'm setting it as 0. If that is equal to northeast, that would have a value 1, else it will have 0. Similarly, I can set northwest, which is NW. Right, this is where I am doing a dummy coding. So instead of northeast, now I'll set this to northwest. Again making it 1 and 0. You already know that if there are n categories in a particular variable which are categorical variable, if there are n categories inside it, we should create n minus 1 dummy variables. So now here there are 4 categories: northeast, northwest, southeast, southwest. So I can create 4 minus 1, 3 dummy variables. 2 of them I have created. So the third one I'll create it as southeast, SE. Again, I can very well consider here southeast. So the fourth one I don't need to create. I have created 3 dummy variables out here. Now let me look at what is coming as a part of summary. Summary of insurance 1, or probably insurance 1. So these are the things that are there. Now it is better for me to remove the second column, and the third, fourth, fifth, sixth column also I should remove, and I think that should be fine. So what I'll do is I'll say insurance 1 is nothing but insurance 1. I'm taking a subset of it. I'll take all the rows, but columns wise I'll remove the columns 2, 6. I'll remove the columns 2, 6. 2 is standing for sex and 6 is standing for region. All others are looking for numerical for me. So I can just remove these 2. Now I can very well quickly look at the structure of insurance 1 to see that all the columns are numerical, and in case they are numerical, now I can very well go with the scaling as well. Insurance 1, I am doing a scaling of insurance 1. So that's how the scaling has been performed on the data. Now again, if you look at the summary of insurance 1, this is what is the summary. Everything is scaled. Now what I can very well do is, now I better split it into training data and testing data. Now that we have already randomly generated the set of values. Now let me call train data, which is a subset of insurance 1, which takes those rows which are there as a part of the train, and it takes all the columns. Whereas the test data is the one which is again a subset of insurance 1, which does not take the rows which are there as a part of the train. So those rows which are not there as a part of the train are considered, and all the columns. So this is how my training data and the testing data have typically come up. Now based on that, now I can start fitting the models. So I'll start different models. One, we'll go ahead with hidden layers, right? So probably let's call fit rprop plus. So fit r prop plus, and I'm putting one hidden layer. So let me take 1, 3, 5 hidden layers. Right? Fit r prop plus 1, wherein I'm using the formula neural net. F is the name of my formula which we have created earlier. The data for me is coming from train data. Right, the data is coming from the train data. Let me set the hidden layers is equal to 1, and the algorithm, let me set it as r prop plus. R prop plus. So this is the model that we are fitting. Fit r prop plus 1. 1 is the hidden layer is 1. Object 6. Okay, F is something now I have to create again. So this is where the problem came. F is charges tilde. I have to take all the other things, age, BMI, children, now smoker, male, NE, NW, and SE. So this is my new F. Right, so this is my new F. Based on that, let me fit the model fit prop plus 1. Yes, there is a neural network that is getting built. So better let me copy this model so that I can do the copying quite easily at a later point. Let me copy this into a notepad. Right, so if I want to change the model later, it's just a matter of changing the things out here. Okay, we have a fit prop plus 1 model, right? And now for this particular model, if I want, I can fit all of them together, right? But let's do the first one first, fit prop plus 1. And once you go back to the slides, okay, get the data into R, done. Response should be a continuous variable, taken care of. Examine the data where you look at the summary, check if there are NAs or missing values in the data. If there are NAs, try some kind of a mechanism of handling those missing values. Then we try to scale the data, which we have already done. All the response variables as well as the explanatory variables, all of them we have scaled. Then we have split the data into a training data set versus the testing data. We have splitting of both 70% approximately into training and the remaining into a testing set. We have stated and stored the form of the model, right? The formula we have stored as a part of F. Now we have fitted the model using neural net. I have the flexibility in playing around with hidden neurons, but right now I have considered only one hidden neuron. But I can very well change the number of hidden neurons, and more. One, I can change the hidden neurons, and I can also actually either increase or decrease the number of hidden layers also. If the hidden neuron is only one, I am considering it as one single layer. But there is a possibility that I can bring in some additional layers, and I have to specify how many neurons are there in each of those layers. So that's also one more kind of a flexibility I carry. But once the model is fitted, I can very well do the plotting of that particular model using plot.nl, which can help me in terms of visualizing the model. So I could very well do fit plot of fit prop plus 1. Right, I have done plot of print prop plus 1. So this is the kind of model, all the input variables, these are the weights, and based on that this is the linkage that is coming to the output variable. So let me store this as well so that our understanding also comes more easier, and next time when I have to change the thing, I'll just change it and I'll execute the code one after the other. So okay, so we have plotted the method. I can also give a print to get the complete overview of the method, right? I can very well give the print of this where I am getting a slightly more overview of this method. Now if you look at the method, here the error is around 106.62, the threshold is around 0.009, and it took almost 57,842 steps to arrive at this particular result with that one node, one hidden layer kind of mechanism. You could see here it has the way it has played around with the weights. You could see some clarity out there, but yes, it got the, I don't have the whole thing out here, so let me just consider this print. Let me store this so that for the next part we can very well use this. So we have printed to get some kind of details regarding the model, where it has talked about what is the total error that has cropped up in the process, how many steps it has taken to finally finalize the result, right? It is giving a kind of an overview of a model. I can also get the summary of the entire result, right? I can very well get the summary of the result, which is nothing but this particular step, which is telling me something regarding the coefficients. If you look at this, the age, the coefficient, the weightage is minus 0.333. Even on the graph, you are able to see that. BMI, the weightage is minus 0.404. It is like this. Then intercept, it is 2.352. That is what is coming out from here. Now once this model has come out here, another intercept is coming from here with the hidden layer. We are mapping it to the charges. So that is how the neural network is getting built out here, which you can easily make out by looking at the result matrix altogether. So we are saying we can very well get a complete summary of the result matrix. Now we can do, once we have the model in place, we can go ahead with the prediction part. But as I have initially indicated, the prediction cannot be done through the predict function out here. We have to do the prediction only with the test data, only with a compute function, not the predict function. Right? I have to use the compute function and not the predict function. So I can very well take that up, right? So let me call pred. Pred is something I'm using the compute function. The model that I'm using is fit rprop plus 1 is the name of the model that I'm using. And the data that I am considering is the test data, wherein I should not consider, I'll consider all the rows, but I should not consider the charges column. The charges column happened to be the 6th column for me. So I'll say all other columns except the charges column is the input to this computation part. So on the test data, I'm removing the 6th column and I'm going ahead with the prediction part. Now the pred has got predicted, so let me save this code as well so that we can repeat it for all of them. Right, we can very well repeat it for all of them. Probably we will try We will try different combination. Right, pred is something where I'm going ahead with this prediction. Once the prediction is done, let me just check what is coming as a part of pred. You could see that what we are getting are a few more things out of this. Pred is giving me one, the neurons, the weights associated with each one of them, and along with that it also gives me the .net result. The .net result is talking of whether the final prediction value is negative or positive. If it is negative, it is like I'm classifying it close to, if it is a classification problem, I'll look at the negative and try to put it under 0. If it is positive, I'll try to put it under 1. Whereas when I'm going in a regression mode, I'll directly take this .net result, and based on that I will try to directly compute the correlation coefficient with the actuals. If you just look at, if I am taking these as predictors, I can very well compute the correlation coefficient between pred dollar net dot result, which happens to be the predicted value, and the actual value comes out as test data and the sixth column from the test data, which is also a kind of scaled version, which is also a scaled one. I'm taking the square of that, and this is telling me that the correlation is hardly to any kind of an extent. Right? It is looking like 0.001. Why is that so weak? Is something that we really need to understand. Pred dot net result is, these are the values that are coming out of pred dot net result, and I can also talk about test data dollar charges. Okay, otherwise I'll give test data, and I'm considering the sixth column. So these are the values that are associated with the test data sixth column. Oh, the sixth column is not the one looks like, because there are only two values. So let me just quickly look at what is the test data, which column. I think I have taken the wrong column. The charges are in the fifth column, not in the sixth column. So this is where I have to be careful of. So let me do the reprediction now. Right, this is what is the prediction that I have to do. Compute fit prop plus 1, and I have to consider all the columns except the fifth column. So based on that I will get my predicted values. Right, let me just check. So these are the predicted values that have come out, and based on the predicted values, now I have to look at the correlation between the predicted values and test data, the fifth column of the test data. I'm taking the fifth column of the test data and I'm taking a square. X must be numeric. Okay, I should take not the predict dollar net dot result. I have to take predict dollar net dot result, right? That is the one that is doing the prediction values. So here it is coming out like 80.31% is the accuracy of this model. So approximately around 19.6% ends up as the error for this particular model. So even let me save this line as well. So these are the 5 lines that will actually help me in terms of executing this model changing the various inputs to it. So what I'll quickly do is a new model that I want to create, wherein everything remains the same. I'll go with 3 hidden layers. Everything else remaining the same, right? The name wise, let me just keep it as it is, but if you want a difference, you keep changing the names. So I'm fitting a model, rprop plus model, with 3 hidden layers. So this is how the model is getting fitted. Okay, the model got fitted. Now quickly I can look at the plot of the model by copying this piece of code. Now this is a very complicated model. You could see that there are 3 hidden layers, and that's how the hidden layers are getting propagated. The error looks like much smaller here, only 66 looks like the error, whereas in the earlier case the error was 106. So it might look positive side, yes, the data has been able to get into a good model, but on the negative side there is a possibility of overfitting to the data as well. So this is where once I do it on the test data, I get things very clear. If I really want some kind of details about it, I can go for the printing of that particular model. But if I'm not much interested in the details, I can directly go for the prediction part. Now when I'm trying to go with the prediction part on my actual data, on my test data, and after that when I'm executing the correlation squared, which is the R squared, it looks like again the accuracy is 80.31% itself, which is more or less similar to the one that we have got with one hidden layer. Hardly any kind of an improvement between one hidden layer versus 3 hidden layers in the whole process. Now if I quickly want, let me change it to 5 as well to see if there is any kind of an improvement in the model. This is a quicker way of doing the execution. Copy your code somewhere so that you can copy the stuff much quicker, and you can execute all the possibilities. I don't want a plot of it. Plot obviously looks very complicated. So if I want, I can look at it, but there are 5 hidden layers, looks very complicated. But what I am more of interest for me is, if I am executing it on the test data, is there any kind of an improvement in the accuracy of the model? So that's the reason I want to test out looking the R squared. Wow, the R squared is looking 87.29%. Now you could see there is a lot of improvisation in the accuracy of the model when we are working out with 5 hidden neurons. That's a layer of complexity that is getting added to the model, but drastically it has improved the prediction accuracy of the model, taking it to 87.29%. Now quickly, if I want, instead of rprop plus, for the same thing I want to try rprop minus, and based on that I want to re-execute the model. So without backtracking, I am looking at resilient backpropagation algorithm without backtracking. Rprop minus is what I have used to fit the model. Let me see if this is in any way improving the overall accuracy of the model. So if it has to improve, it has to increase from 87.29%. So this is where I can play around, one with different number of hidden layers, two with the different algorithms, and at the same time, if I have an option, I can also bring in the error function. I can play around with either SSE, sum of squared errors, or cross entropy. I can also work out with the activation function where the default one is logistic, but at the same time I can also give tan h, which is a hyperbolic tangent kind of a function as well. Oh, here it looks like the algorithm did not converge. If I am going with rprop minus kind of stuff, right, it did not converge. So which means I could have tried the number of steps to be slightly higher. But let me quickly check. Okay, weights are not calculated, so there is no way in which I can go ahead with this algorithm here. So let me see if by reducing the number of hidden layers, or I have to increase the number of steps. Even that's one more option that is there. But let me just check if I am decreasing the number of hidden layers, is it in any way able to execute it? Okay, for 3 hidden layers it is able to execute the stuff, and this is how the plotting also came out. Again, another complex plot. I am going ahead in terms of doing the prediction with respect to the actual data. The prediction is done, and probably I can very well do the correlation squared, which is the R squared. Again, this model resulted in 86.91%, slightly lesser than the with respect to 3, but the improvement is much better, 86.91, which is much higher than the 3 hidden layer formula which we had for R prop plus. Right, the same way, instead of R prop minus, I can also play around with SLR, which is the slowest learning rate kind of an algorithm, all else remaining the same. If I'm going with hidden layers, 3 hidden layers, I really want to check with the slow learning rate, is there any kind of an improvement in the accuracy on my testing data. So on the training data, I can look at by looking at the error part, but on the testing data also I would like to check this out. Okay, even this could not converge, so at least let's increase the number of steps, right? The step max, even with this much, it's not able to converge. So probably I need to increase the step max. Let's try this out. So I can actually bring in the step max as 1 million. So initially it is 100,000. Now I can increase it to 1 million to see if there is some kind of a convergence that can very well happen. Because the learning rate is very slow, the number of steps that it will take for convergence is much higher. We need to understand that. So once we have increased the number of steps, I think there is a convergence that has occurred. So once the model is fitted, I can very well look at the plotting the model with the slowest learning rate. Now you see there are almost 215,000 steps that it has taken. but the error rate is around 69, slightly higher than the earlier case of rprop minus. But only when I am doing the testing with the test data, I'll get a clarity on which one is better off, right? So the prediction is being performed on the test data. Now I can find out the R squared between the actual versus the predicted value. Wow, it has gone up to 89.21, which is a very good indication that for this kind of a data, going with the slowest learning rate algorithm with the 3 hidden layers has really done the job for me. But what if I increase the hidden layers to 5 in the same scenario, wherein I can increase the step max to 1 million, and I really want to check out whether this will work in case of 5 hidden layers. Is there any kind of an improvement that I am going to get in the model? So that's how people typically take things further in terms of improvising the models to see any better model comes up with increasing the number of hidden layers, or with changing the algorithm, with changing the error computation, because here 89.21 on the testing data is a simply superb kind of a mechanism, because the one hidden layer kind of mechanisms were giving us an accuracy rate of 80%, whereas here it jumped to the extent of 89.2%, which is improving the prediction accuracy of our model. Now I want to see if changing the number of hidden layers to 5 and continuing with the slowest learning rate mechanism itself, can it improve the overall accuracy of the model? Looks like the number of steps that are taken for execution of this is far more higher than 215,000, which it has taken in case of 3 hidden layers. There is a good chance that this number could even cross the 500,000 number of steps. That's where probably we could see that there is a huge amount of time that is going in terms of building the model itself. Once the model gets built, everything else is straightforward. We have to test this on the testing data and see to what extent the R squared of the model has actually improved. Now this model fitment is done, we can very well look at if there is any kind of improvisation. First, let's look at the plotting of this. Plotting, very complicated plotting got created. Now let me tell you, in all these cases we have still said the hidden layer has only one layer, but sometimes what people do is they'll set even the hidden layers as 2 layers with different number of nodes in each of the hidden layers. Even those kind of scenarios should basically be planned out. So that's how the old set of models are being planned out, by knowing what are the kinds of variables that we have, what is the kind of customization that we can perform. That would give me the base for trying out all possible values, which can overall result in improving the accuracy of my model to the core. Now when I am looking at R squared here, oh, it has fallen. So which means 5 hidden layers have not done any kind of a good job for me. Only there's a lot of overfitment that has happened. But 3 hidden layers with SLR algorithm it has given me a good kind of overall fitment, 89.21% being the overall fitment to the testing data. So out of these three models, if I have to narrow down, and based on whatever the various scenarios that I have tested, I would be preferring the smallest learning rate kind of algorithm with three hidden layers as the basis for the prediction using these using if I have to use one of these three models. But at the same time, I can very well work out on the other methods. If required, I can even go into the plotting between the actuals versus the predicted values. And now I need to really focus on, apart from these three models that I'm looking at, what could be the other models which I can very well use in the context of neural networks itself. And if I'm using any of those models, is there any way I can still improvise the accuracy of the model from that 89.21% which I have got in the case of slowest learning rate algorithm with three hidden layers. So we have three more algorithms to look at in this context. We'll execute all of them on the same data. So let's get into the next process. The next algorithm, which is the general regression neural network. General regression neural network is the kind of algorithm that we will be using for the prediction of a numerical variable, which is the insurance charges based on the parameters based on the variables that we have already discussed earlier. All right. Now, getting on to general regression neural network, this can be implemented using the package grnn, and within that we have a learn function. So let me first install the package grnn, which represents general regression neural network. Install.packages grnn. All right. Okay, this package is installed. Let's load this package, grnn package. And within this, there is a function called learn. So we are going to look at this function learn. Learn is a function that is coming from grnn package. It creates or updates a general regression neural network. Earlier we talked about PNN in the case of classification, which is called as a probabilistic neural network. Here equivalently we are talking about a general regression neural network, wherein a learn as a function, it takes set as an input. Set is nothing but it's a data frame representing the training set. The first column is used to define the category of each observation. Here also we require the first column, which is representing the category of each of the observations, which is the Y part. And then we are talking about a neural network, which is a general regression neural network. And if at all the first one is not the column, then you have to use variable.column, which talks about the field number of variable. By default it is 1, but if it is not 1 in our data, either I can bring it to 1 and I can omit this field. Otherwise I have to set this to the number which particular column is my response variable. So that is how we are creating a general regression neural network, which we can do it on our same data. Right, we can use the same insurance data for this purpose. The only thing now is the variable that we are looking at in this case is the charges, right? That's the variable that we are looking at in this example. So we have broken up the data into training data, testing data, all those things are already taken care of. So we can very well fit the GRNN basic model because it also involves the smoothing process. But let's quickly see. So we have to give the response variable and the explanatory variable. Probably all I can do in this case is I can give the whole data frame as a part of the set, right? As a part of the set, I can give all the entire data frame as an input, and as a part of variable dot column, I can specify that particular column. I think it's the fifth column that is typically having the response variable. So I can very well give that column number so that it can pick up the fifth column as our response variable. I'm loading the GRNN package, done, got the data. So because we are using the same data, I don't need to do these things again and again. We have split the sample into the training data as well as the testing data. The form of the model has already been stored. Then model is fitted using learn. So this is where we are. So I can very well use fit learn or fit grnn. No, let me say fit learn. After smoothing, I'll call it as fit grnn. So we have a learn, the learn model, wherein I have to consider the data frame, right? The data frame which is already I will take train data directly, but I have to give the variable. So let me just see what is the summary of the train data so that I will have an understanding of where exactly my charges are. Charges are my fifth variable, right? So this is where I can say fit learn is using a parameter called learn, is using a function called learn, wherein my data is the training data. So NN is nothing, sorry, my the input that we are giving into it, set is nothing but it is the train data. So let me, I can also say set equal to train data, and I don't need to give the neural network anything, general regression neural network with training or without training. And I can give the variable dot column. I will set it not the default value of 1, I will set it as 5, the field number of the variable. So the response variable is what I have to give here. So this is where I have set it as 5. Now this is the learning that has already occurred. Let me see what the learning has typically come out as. You could see here in some of the input, okay, there are 8 columns. The $K is saying that there are 8 explanatory variables that are considered, 937 records that are considered for the input purpose, and a few things are missing out here. Okay, so that's the important information that we have. So we can also do the smoothing, as if you remember, we have used a function called smooth. If we quickly look at what this smooth is containing, smooth, now I'll take it from the grnn package. So it will take NN, which is a trained general regression neural network, as the input, and sigma is a scalar. So it's more and more for the optimization purpose. The smoothing is basically to smooth the general regression neural network. So we will smoothen it. We will try to fit grnn is the name of the model that we are calling. We'll use the smooth function where we will say fit learn is the name of the original general regression neural network model, and the sigma, for the time being, I can ignore it so that I want the system to bring out the optimal value of sigma. error in smooth fit learn, because the sigma also is a required value. There is no default value that it is. So in that case, I will set the sigma value as, let's say, 2 or something. So based on different values of sigma, again I can do the smoothing process out here. So now if I look at fit grnn, again there is a generalized linear regression network that is being built, a neural network that is being built with a sigma value of 2. I can keep changing the value of sigma and I can get different kinds of results as well. So that's one thing. We have fitted the model using the learn. Then we have used the smooth method to generalize the smooth, to smoothen the general regression neural network. Then for the prediction purpose, again the same logic. First thing is I will predict only for the first row, and after that here we will be using the guess, just like your probabilistic neural network. If you look at the guess function, infer the value of a new observation, wherein the input that I am giving is a trained and smoothened general regression neural network. So I have to give it as a fit grnn and a vector describing a new observation. So this is what I have to give as an input to this. So this is where, if you see, I can give the input as guess. The first thing I'll give it is fit grnn, that's the name of the function, and the data wise x. The x that I have to provide here, I'll take it as a matrix. The first observation, which is coming from the test data, I'll take it from the test data, the first row and all the columns. So this is what is the data that I am taking from the test data. The first row is what I am considering, and I'm converting it into a matrix. So that's where I called it as dot matrix, and I've got a guessed value. Now I could see non-conformable arrays. Why is that? Now there are more than 50 warnings to see. Okay, I should not give the first, I should not give the charges column. So this is where I'll say -5. The fifth column I would not give because that's the output response variable. I should not give it as an input variable, right? So that's the reason I think it has given me an error. So let me quickly look at what is happening. Non-conformable arrays. Let me quickly check what is coming out as test data 1 comma -5. So this is what is coming out as a part of the test data 1 comma -5. So these are the inputs that are coming up. Fair enough. The fit DRNN is also coming out. So these are the numbers that are there, and I can very well get the guess part. The guess fit grnn. Why is this is giving me non-conformable arrays? Let me just remove the x equal to here. Hmm, what could be the reason out here? How did the fit grnn got created? If I look at fit grnn, it is containing 8 columns with a sigma of 2. So these are the typical predicted values that are coming out of this fit grnn. Right, YA values are coming out in this way. These are the YA values. So we have this number of values coming out as YA values. Hmm, how do I change it? So I'm getting these as my YA values with the training data. Now I should apply the model. So I need to give vector describing a new observation, guess NN. NN is a trained and smoothened general regression neural network. So I can very well give guess fit grnn, that's one input, and the second input I have to give is the test data. From the test data I am taking the first row and all the columns except the fifth column. So this is what I am taking as an input. Now this is saying non-conformable arrays. Even if I change this to as dot matrix, so array size is becoming a non-conformability, looks like. So the number of variables that have come out looks like no, but there are 8 variables itself. So there is no question of non-conformability in the patterns. Let me quickly run through the model once again, right from the first step. Let me quickly run through the step to make sure that I did not miss out anything. Right, I have broken the data into a training data and a testing data. So let me look at quickly the head of train data. So we have 9 columns. Sim of train data also, let me look at it, which is containing these 9 columns. Right, just to make sure, let me bring in this charges to the first column. I think that sometimes that is necessary. Let me just quickly bring this charges to the first column. So I'll call train data as cbind, wherein I am doing train data dollar charges, and to that I am actually bringing train data all the rows without the fifth column. So I'm doing this so that the fifth column is coming to the first column. Okay, so the dollar is not working out here. So instead of dollar, let me just set train data dollar the all the rows comma fifth column comma train data all the rows minus the fifth column. So this is what I'm trying to bring in as a part of the train data, and I could clearly see now the head of train data looking like, oh, I have to put the headings for the first one, right? So names of train data, uh, names of train data, the first index, let me set it as charges. Well, charges, I'll put it under quotes. So now let me just check the head of train data. So this is the names. Names of train data. So let me just check names of train data. So this is where the whole thing got messed up. Right, the whole thing got messed up out here. So let me initiate the process once again. Uh, we have insurance 1. Let me just check what is there as a part of insurance 1. So this is what is there as a part of insurance 1. So what I want to do is I'll bring the fifth column as the first column, right? So I'll say insurance 1 is, I'm bringing in C bind, wherein I'm saying, or let me set it to insurance 2 so that I don't make a mistake. Insurance 2, I'm setting it in such a way wherein I'm bringing C bind, insurance 1, taking all the rows and the fifth column, right? That I'm considering all the rows and the fifth column. Along with that, I'm also appending insurance 1. So there's a C bind that I have done. Now doing head of insurance 2 has given me this, wherein now I can make very well set names of insurance 2. Okay, that is coming out to be null. So what I do is insurance 2, when I'm doing a C bind, let me do as dot data frame of this. I'm doing an as dot data frame of this. So let me just check now what is happening to head of insurance 2. Yeah, now this is better. It's coming out as V1. So now when I check the names of insurance 2, it is coming out as V1. So I'll set names of insurance 2 and the subset I'm taking it as 1, the first one, I'll set it as charges, right? So this is what I'm setting it. Now I'll say insurance 2 is nothing but insurance 2 and a subset all the rows without the sixth column. Now let me quickly look at the head of insurance Q to make sure that everything is fine. Now from here I'm splitting my training data. The training data for me is nothing but I am taking a subset from insurance Q where I'm considering the rows which are there as a part of the train and I'm considering all the columns. And test data for me is again it's a subset of insurance Q where I will not be considering the values that are there as a part of the train and I'll take all the columns. So I have my training data and the testing data in front of me, right? So I have my training data, I have my testing data with me. Now I am doing a basic fitment. So I am calling it as fit learning model, wherein I am doing a learning, and the learning that I am doing is based on this data frame, which is the train data. I don't need to give the variable name here, the variable column, because the first column is containing the charges. So I am doing a fit learn just with this simple stuff. My model has learned a little bit. Now I want to do the smoothing of this by using the smooth function. So I am using the smooth function wherein I am giving the fit learn as an input to it, and probably the sigma value I can very well set it to my requirement. Here I have set the value to be 2. Now based on this I have got my fit grnn. So probably if I want to look at some basic aspects of fit grnn, you could see that it has taken the k value as 8, and this is how your fit grnn has finally come out after the smoothing process. Now we want to guess on the test data. So this is where I want to use fit grnn, and the data wise now I want to use the as matrix test data without, so I'll consider all the rows but I'll not consider the first column. So this is what I want to consider as a part of my test data, and I want to do the fitting of the model for this. Now it is doing the fitment. Probably there is a problem with the data frame from my training data. So that's where I think I had landed up into trouble earlier. But now the guessing part is being done quite comfortably. Error: cannot allocate vector of size 1.1 GB. So the size is looking like a problem out here, right? So that is where probably we may not be able to work out on this because of the size problem. If I don't do as dot matrix, right now you could see that the fitment is coming out proper. So it requires a matrix. So here the data is looking quite heavy, so that's the reason I think the fitment is not happening properly. But otherwise once you have a slightly smaller set of data, I think you should be able to work around with it, because here cannot allocate vector of size. So that's a different error altogether, which has nothing to do with the accuracy of the model. So you can very well take some other data set. Now once you have got it for one of them, you can do the repetition, you can do the looping for all the values from the test data by ignoring the first observation, first column. And after that, once the prediction gets done, you can very well compare the actual with the predicted values, find out the correlation squared, which is the R squared, on the testing data, and based on that you can very well assess the accuracy of the fitment of the model. And if this comes out to be much higher than what you have got using your earlier methods, this would be the more and more preferable method for the prediction purposes. So that's how we can evaluate the generalized general regression neural network model. In this case, the size is becoming a big issue, so that's where I cannot use it for this particular example. Right? For smaller data sets, probably you should try the model out again. All right. So now, right? So this is how you are looking at. Initially, you are taking the first response, first test data. Based on that, you are doing the guessing. If you have got the response properly for the first one, you are looping it across all the observations of the test data. We had 401 observations. So we would be looping it across all the 401 observations of the test data. And based on that, either I can use a scatter plot to do the plotting part, or I can use the correlation squared to get the R squared value between the predicted values and the actual values. And based on that, I can very well talk about the efficiency of this particular neural network for the numerical value prediction. Now, the next model that I am going to touch base here is a monotone multi-layer perceptron. This is more and more helpful, especially when we have this monotonicity kind of behavior in our variables. A monotonically increasing behavior of the response variable for some set of attributes, right? For some set of explanatory variables, I want my response variable to keep increasing in value only. It should not fall. For as the value of my response explanatory variable or the attributes are changing, I want my response variable to keep increasing itself. I don't want it to fall at all. So this is where we are talking about monotonically increasing behavior of the response variable with respect to different attributes. Some specified attributes, I want my response variable to keep increasing only. There is no kind of falling of the response variable. And in such kind of scenarios, I can very well take the help of monotonically increasing behavior, which can be obtained through monotone multi-layer perceptron. So here I would be able to train the model and make the predictions by setting some constraints with respect to partial monotonicity. And that particular behavior is very much accomplished through MON-MLP, monotone multi-layer perceptron. So we are taking the MON-MLP package, and in that we have a function called monmlp.fit. So let's install that package to get more and more clarity on, and we will even look at the function to get even more clarity on what that particular function is doing for us. Okay, so the monmlp package is installed. Let's load this monmlp, which is the monotone multi-layer perceptron package, and within that now we are talking about a function called monmlp.fit. So which is the word itself is very clear, the function is very clear. We are trying to fit a monotone multi-layer perceptron. For MON-MLP model or an ensemble of MON-MLP models using the NLM optimization routine, nonlinear methods, optimal stopped training and bootstrap aggregation, which is the bagging, can be used to help, bagging can be used to help overfitting, avoiding the overfitting of the model. So this is what we are to look at. If I am trying to fit a monotonically increasing response variable using a multi-layer perceptron, mon mlp.fit, I have to give the x and y. X is a covariate matrix. Look at this, covariate matrix with number of rows equal to number of samples and number of columns equal to number of covariates. So it should be a covariate matrix. Number of rows are typically equal to the number of samples and number of columns equal to the number of covariates. So this is where I am taking only the training data and I have to consider only the covariates that are there. Similarly, Y is a predicted matrix with number of rows equal to number of samples, number of columns equal to number of predictants. So basically now I have to split my X and Y. So X I will take it as, as dot matrix. I'll convert it into a matrix, right? Where the data frame that I am taking is train data. Within that train data, I am taking all the rows, I am taking all the columns which are not, but the one that is not there in the first column, which is I am not taking the output variable from the training data. So this is what I am calling as X. Now if I am looking at the dim of X, it's 937 rows, 8 columns. If I look at the head of X, it contains only the age, BMI, children and so on. Whereas Y I will be considering as dot matrix, again from the train data, right? I would be considering from the training data itself as dot matrix. From the train data, I would be considering all the rows but only column number 1. So that's how I have separated my X values and the Y values. So if you look at the dim of Y, it shows me 937 rows and 1 column. So if you now look at X, which is a covariate matrix with number of rows equal to number of samples, number of columns equal to number of covariates. Y is a predicted matrix, number of rows equal to number of samples, number of columns equal to number of predictants. So we got the values of X and Y from the training data. Now the same logic I may have to apply it on my testing data as well. So I will consider the same as dot matrix, but here instead of train data, I'll call it as test data for my X1, and similarly I will consider the same for Y1 as well from the test data only. I'll again consider the as dot matrix, right? Instead of train data, I will take the test data. So X1 and Y1 are my testing data, X and Y are my training data. So now I think I am in a position to do the fitment, but before that let me see hidden 1, hidden 2. So how many nodes are there in the first hidden layer? How many nodes are there in the second hidden layer? So the first thing I have to specify. The second thing, if I don't specify, it is optional. By default it will take a value of 0. Then I have to also specify maximum number of iterations that it is going to take. So by default it is 5000 iterations, but if I have to increase it something more, then I have to increase the number of stuff. So the number of trials, to avoid the local minima, if I have to increase the number of trials, I can do it using n dot trials. By default it is 1, but I can very well increase the stuff. Number of ensemble members to fit, by default it's 1, but I can increase it to any other number. The most important part for me here, if I really want to do the scalings per Why? By default, we are anyhow giving a scaled version, but even if I don't give a scaled version, by default it is going to do the transformation of the scaled version. Why? More and more important is the monotone. Which variables I want them to be monotonically increasing. For which variables I want my output to be monotonically increasing. Column indicating the covariates for which the monotonity constant should hold. If I want, I can give for all the variables. So I have 8 variables in this example. So I can very well give all 1 to 8. So using this as an example, so probably here the only thing that I can modify is monotone. I can change only a few variables as monotonically impacting, and I can actually play around with the number of hidden layers. So right now let me go ahead with the fitment of this particular model, where I'm using mon mlp dot fit as a function. Now on this, I need the x, so I can directly give the value of x. I need y, which is my output, that is response variable regarding the training data. Then I have to give my hidden one, how many layers I want as a part of the hidden one. Let's say I'll give 3 layers. Hidden 2, if I want I can give, so let me just give 1, otherwise by default it will be 0. And I can very well set the monotone value. Probably let me take all the 8 variables as monotonical constraints. Then n dot trials, it's better to make sure that there is no local minima that is coming. So I can set n dot trials equal to 5, and I think all others I can leave them to be right. It is talking about number of trials to avoid the local minima. And if I want, I can also talk about number of ensembles to be fitted. By default it is 1. So if I want to change that as well, n dot ensemble, let's say I can very well set it equal to 3. And similarly bagging, if there should be some kind of gradient, right, whether we are talking about bootstrap aggregation gradient. So if I want that bagging to be done, I can very well set it to be true. So I can very well go ahead with number of trials. Probably instead of 5 we can also set some big values. Right, this I can set it to 100, ensembles I can set them to 50, so that I'll get some clear cut difference in the solution that I am getting. And even if required, the bag I can very well set it to true as well, so that the bootstrap aggregation is also typically performed on the data. Now with this we can go ahead in terms of fitting the model. The model will take some amount of time for the fitting process, because we have different values of x, y, 2 hidden layers, 3 nodes in the first hidden layer, 1 node in the second hidden layer. Now you have so many options to play around with. So here, as a predictive modeler, we keep on trying all these kinds of models on the data, try to see which model is giving a better learning from the data. And apart from learning from the training data, if I am trying to work it out on the testing data, which one of these models is showing a good amount of accuracy, that is also something that we are more and more relying on. So here we are making an assumption that all the 8 variables, they have to keep our response variable value or monotonically increasing itself. I cannot see that any of the response variable can be decreasing with any one of these 8 attributes. So that's the kind of risk that we have taken in the process, right? But that's okay. In case I really want to check out, it would be much better for me. So let's see until it executes. it's taking too much of time for fitment because number of trials is much higher. Ensembles is also 50. But yeah, we have the flexibility in terms of changing all those values. And but our main objective is I should get a much better prediction when I am doing the same on the test data. Let me just pause it until it gets executed. Looks like a lot of errors are cropping up in the process. So let me just pause this and let me simplify it without considering all these variables at all. Let me take a simple model and see whether it is going to work in any way for this data. Let me execute it quickly and see without doing any of the, yeah, here it is coming out with one single ensemble. It is coming out to be decently fit. So we have to increase the iterations and we may have to play around with the number of ensembles to be fitted, number of trials to be executed so that the local minima does not come into picture. But once we have got the fit, let me see what is that I can derive from this fit. So the fit is giving me, with respect to the training data, there is a kind of a fitment that is being performed. And now if we want to look at the different attributes that are given by the fit, right, I have to look at the different attributes that are given by the fit. We could see that it gives me the values of y, the value of y predicted. We are going to get all those values. So let me just check attributes of fit, and if I put $y, I'll get the y values associated with all these 937. Similarly, I can get y dot pred, which is the predicted y. So I can take the correlation on the attributes of fit $y versus attributes of fit $y dot pred. I can take these two things, the predicted versus the actual values, and I can take a square of it to get the r squared on the training data. So it works out that using this model, the r squared on the training data is to the extent of 83.37%. Now I want to really test this out on the testing data. And for working out on the testing data, okay, so here let's do the process. We have loaded this, we have taken care of this. This is the same data, so these steps are already taken care of. Now we have built, okay, here instead of one hidden layer network, for our example, we have built a two hidden layer network. 3 nodes in the first layer, 1 node in the second layer. And I have set monotonic constraints as all the 8 variables as monotone constraints or attributes. Though we wanted to increase the number of trials and number of ensembles as well as the bagging set to true, it looks like the amount of time that it is taking to execute is much higher. So depending on the kind of system capacities that we have, I think we should go about usage of these kind of mechanisms. Then once we have got the fitted values, I have taken the correlation coefficient or R squared. This is with respect to the training data. So the training data, we have got the R squared value as 83%. Now I can go ahead with the testing part. For the applying on the test data, I'll use the function called monmlp.predict. Let's see what this is doing for us. Monmlp.predict is actually making predictions from a fitted MonMLP model or an ensemble of MonMLP models. Here it's only one single ensemble. So we are taking the already fitted MonMLP model, and based on that we are trying to do the prediction. So X is a covariate matrix. Number of rows is equal to number of samples and number of columns equal to number of covariant. That is what we are calling as X. In this case, for our test data, we have already called it as X1. Weights is a list containing MonMLP weight matrices and other parameters which are coming from MonMLP fit. So I can very well use the fitted variable for that. So I'll take the pred as the name of the variable out here, which will do monmlp dot predict. The input I am giving as x1 to it, and weights I am setting it equal to fit mlp, or probably we have called it as just fit, right? So let me use the word fit. So based on that, the prediction has already been performed. Now I can very well do the correlation between the predicted as well as the actuals. The actuals I have already captured as a part of y1. y1 squared. I will take the r squared between the predicted and the actuals. Here it is working out to 86.12. Whereas in one of the earlier models we were able to strike almost 89 as a part of the r squared on the test data, the same set of test data. Whereas this particular model, which is monotone multi-layer perceptron model with one trial which might be a local minima, along with we are also gone with only one single ensemble. So that way the model probably could have been improvised by changing the number of trials and number of ensembles, and based on that repeating the whole process of prediction, which might increase our R squared on the test data. But with this model that we have gone ahead with, the R squared on the test data is lying out to be around 86%. So even this is one more model that could help us in terms of doing the predictions for numerical variables, right? So you could see that there are different kinds of models for doing predictions with numerical variables. So we should be comfortable in terms of working out with monotonically increasing attributes associated with the response variable. Multi-layer perceptron model is something that I can very well fit to the data. Now, coming on to one more important model regarding the numerical prediction, I'm talking about a quantile regression. The word is very clear. I will set some number of quantiles, probably a 5 percentile, a 50 percentile, a 95 percentile, some kind of quantiles I am going to set, and I am going to perform the regression at each of these different quantiles. So it is modeling the relationship between the independent variable, which in our case is the insurance charges, and the conditional quantiles of the response variable. So I would be taking 2 or 3 different quantiles for the response variable. So, sorry, the independent variables here are the 8 variables that we are talking of, right? And those 8 variables, we are trying to find the relationship with respect to the conditional quantile. So, I may be taking the 5 percentile, the 50 percentile, the 95 percentile, or sometimes I would choose 25 percentile, 50 percentile, and 75 percentile. So, I would try to look at the different quantiles of the response variable, and for each of the quantiles of the response variables, I'll try to find out the relationship with respect to the various explanatory variables. So this gives me a very comprehensive picture of the conditional distribution of the response variable, because we can very well give different kinds of quantiles. If I'm more bothered about the extreme values, I would look at the 5 percentile and 95 percentile as the quantile. Whereas if I am more bothered about the mean behavior, I can go with 25 and 75. So I can very well give the lower quantiles, upper quantiles, and depending on the kind of interest I have, which means I can track the overall distribution of the response variable quite comfortably by going ahead with this quantile regression based neural network. And for that we are using a package which is QRNN, and the function that we are using is qrnn.fit. So let me load the packages. QRNN, which is quantile regression neural network, right? We are loading this package as well. Now based on that, we require to know what is the function qrnn.fit is doing for us. Now here it says it's a function used to fit a quantile regression neural network model, or it's an ensemble of models. So ensemble is again like multi-starts and multiple models being built with multiple starting point. So either I can build one single model, or it can give me a package of models first. But if you look at the input, more or less it is similar to the earlier one, which is a multi-layer monotonously increasing multi-layer perceptron model. If you look at the function x, it's again a covariant matrix with the number of rows equal to the number of samples, number of columns equal to number of variables. Y is again a predicted column matrix with the number of rows equal to number of samples. So x and y are more or less similar. I have to give number of hidden nodes in the QRNN model. So I can very well specify how many nodes I want as a part of the QRNI model, and the quantiles that I really want, I have to specify it as a part of the tau quantiles. So I have to specify what are all the typical quantiles I require. So all those things I can specify as an individual probabilities, and based on that I can go ahead in terms of fitting of the model. And a few more things I think of in terms of the fitting here. So I have to give the values of x, I'll give the value of y, how many hidden layers do I require, what are the various quantiles for which I want the model to be fitted, how many iterations have to happen. There are 5000 iterations, which is the default. Number of trials by default is 5, I can go ahead with it. Number of ensembles, by default it is 1. If I want to go ahead with it, I can go ahead, otherwise I can increase it. But to start with, I can very well go ahead with the defaults itself, except for something that are mandatorily required. So here my x and y are already there in place. So I can very well go ahead first specifying the quantiles. So I'll call them as probabilities. So I'll say I want let's say 3 or 5 different quantiles. So one I'll set it at 5 percentile, 25 percentile, 50 percentile, 75 percentile, and 95 percentile. I'll set for these kind of probabilities. So what we typically do here is, in the modeling, we will set both the fitted values and the predicted values, both of them will take it as a list. So I'll say fit as well as predicted. Both of them, I'm setting them initially as empty lists. The reason is, depending on, now here I have 5 different probabilities. So I will loop the process 5 times. I will fit the model 5 times. One with a probability of 0.05, one with a probability of 0.25. So that's how I will go ahead in terms of fitting the model. Right? I will get 5 different models. So it's as good as saying it's as good as either I do it this way or I put separately. Fit 0.05, right? Fit 25, fit 50, fit 75. I give different kinds of names, and even there I can go ahead with the prediction process. So I can very well do either of the processes out here. So let me go ahead in the normal way itself, right? Otherwise you can do the looping process. So let me go with fit 05, wherein I am considering qrnn.fit, right? I am taking qrnn.fit. X value is the X value itself, which is the covariates from our training data. The Y is the response variable from the training data, so I'll keep it as it is. Then n dot hidden is something that I can very well set. Let's say I want 3 layers as a part of my hidden. Then tau, I can very well set it to 0.05. This is what is the difference. The tau is what I am setting it as 0.05. Rest all I can continue them as it is. So this is my fit 05 model. So which is at quantile 5 percentile, this model is getting fitted. For 5%, this for 5 percentile, this particular, so it will take the 5 percentile values from the data, and based on that, quantile neural network is getting fitted. So this is how the tau value has started with, and from there the parameter values got improvised and finally resulted in this particular value for fit 05. Then similarly you can very well set it as 25 percentile, and I'll call it as fit 25. We are getting a different model for 25 percentile. So these are the values associated with 25 percentile. So if I am trying to just plot or probably find out what is there as a part of fit 05, these are the things that are coming out. These are the weights, right? This is how the process has gone ahead. The minus infinity, then we are getting the sequence. The tau value is 0.05, and this is how the whole process has come out, and these are the y centers and x centers, y scale, and the x scale values that are being produced. So this is how the 0.05 quantile or 5 percentile value has been modeled. Similarly, for 25 percentile, we got a different model. Now I can go with a 50 percentile to get a different model altogether, the quantile regression neural network model. Now, which means for each of the quantiles, we are getting a slightly different model that is getting built in the whole process. We are getting a different model that is getting built. Right, so this is for the 50. Now if I really want to do the plotting of this fit 50, anyhow this is not supporting, the model is not supporting for that. Now let me again go with 75 as well. This is only with one single ensemble. I'll go with fit 75. Now I can even do the prediction for each of the quantiles as well. So this is associated with the 75, and probably I can also go with 95. Right? So we have all the 5. Now I can very well look at the prediction. I can very well do the prediction of 5 percentile value. I can very well go with 5 percentile, where I would use qrnn dot predict by considering the x1, which is my training data or testing data, and I will fit 05 as an input to it. Now based on this, my pred 05 is getting computed, and now if I quickly check my pred 05 by taking the head of it, so we are talking about going with the worst case kind of a prediction. So the pred 05 predicted values are coming out like this. Whereas if I am talking of pred 25, right, if I am talking of pred 25, the fit 25 model is being fitted, and if I have to look at the head of pred 25, I am getting a completely different set of values out here. Right, so going with pred 25, the model values are different, so that is where now I can change all of them. I'm getting a pred 50 based on the 50 quantile 50 percentile values. Similarly, based on the 75 percentile model, I'm doing a fit 75, which is a prediction of 75 related value, and I'm also going with 95. So I have 5 different predicted values that have cropped up altogether. Now if required, I can bind all of them as well. Right, now what I can very well do is pred. I'll call it as a C bind, wherein, or let me yeah, I can do a C bind, or probably let me call it as dot data dot frame. I will do a C bind pred 05 comma pred 25 comma pred 50 comma pred 75 comma pred 95. I'm doing a C bind of all of them, converting that into a data frame. So if I look at the head of pred, here I'm getting right from the extreme most value. So for the first one, the range is anywhere between minus 0.98 to plus 0.55. We are able to get that kind of a quantile for the first observation. For the second one, it is between minus 0.77 to minus 0.17. For the third, the charges could be anywhere between minus 0.51 to plus 0.78. So I'm getting the ranges, the minimum most to the maximum most kind of stuff. But if I really want to go ahead with the correlation, I can look at this V3, which is corresponding to the 50 percentile stuff. So I can very well look at the correlation between pred 50 and the actual values are coming out with Y1. I'll take pred 50 and y1 and I'll take the square of it. So 86.77% is what is the accuracy of the model that is coming out on the test data. So now we could see, so here apart from just the mean value, I can also do the extreme. There is a possibility that the charges for the first one can lie anywhere between minus 0.98 to plus 0.55, whereas yes, the 50 quantile stuff is 50 percentile stuff is very much saying that it is around minus 0.95, whereas there is some possibility that it can go to the extent of plus 0.55 also. Even the 75 percentile is showing as minus 0.75, but there is some simple chance that this number could go to the extent of 0.55. The same logic we are trying out for each of the observations, minus 0.51, minus 0.49, minus 0.51, minus 0.49, but the V5 is suddenly saying that it is going up to 0.78. So this is on the most higher side, this is the most the lower side, and based on the median value or the 50 percentile value, we are trying to do the prediction with respect to the actuals and trying to see the R squared of the model. So overall, if we see in all these models, right, quickly looking at the process, I think we have taken care of the process quite comfortably out here. For each quantile, we have fitted the model. A separate model is coming out for each quantile. I could have used a for loop to repeat the process across all the quantiles, and because we had only 5 different possibilities, I have individually executed them also, but I could have very well tried it as a kind of a looping process to save our time and save our mistakes in terms of creating the model. Now for each of the quantiles, we have used qrnn.predict with the fitted model. So 5 different fitted models for 5 different quantiles. So the prediction values are also different for each of the quantiles. Now I use the 50th percentile or the median values, and based on that try finding out the correlation squared or the R squared value to try to assess which model is more and more a better fitment for the data. So you could see that within the neural networks there are quite a good number of mechanisms that are available, and there is no theory which says this mechanism is always better compared to this. So the only thing is we need to get a good understanding of all the different kinds of mechanisms and build a very sufficient testing data, build the model from a training data containing 70% of the observations, run it on the testing data, and based on that you could assess whichever is the one giving me a very high level of accuracy on the testing data would be the model for my choice. So that's how we can look at all the 6 different mechanisms that we have discussed. For each of these algorithms, when you are implementing it in R, we could see that there is some level of flexibility, there is some level of customization that you can do with respect to some of the attributes that you are giving to the model. So within the 6, you have so many such kind of customizations that are available, which means you could build a few tens of few dozens of models by taking all these 6 different algorithms and various customizations within these algorithms. Now our objective is to test all these algorithms, the models that are built with the same training data on all these algorithms, test them out on the testing data which is again uniform across all these algorithms, see in which of the cases the R squared of the models are coming out to be much more appropriate. So that's how you go ahead in terms of evaluating each of the models using the different regression algorithms associated with neural networks. So that is what I wanted to cover as a part of this session. If you have any further queries, you can very well get in touch with me by giving me a call on any of the number that I have provided below, or you can send in an email at vamsidhar@pagegurus.com. Thanks a lot for listening to this session. Thank you very much.